Hi everyone, I'm PialetGhorayeb. I just started a postdoc at the University of Chicago. And today I'm excited to tell you more about where we're at and what exciting things to look forward to in terms of the search for secondary atmospheres on small rocky exoplanets. So to begin, I'd like to start with thinking about the types of secondary atmospheres that we know of around rocky worlds. They have a lot of diversity in how thick these atmospheres are, whether they're cloudy, hazy, or mostly clear, and also their composition, which molecules make them up, with very oxidized composition, like for a planet like the Earth, or very reduced compositions for something like Titan that has a lot of methane. But one thing that they all have in common is that they're all around the same star, the Sun, and we have yet to conclusively detect an atmosphere around a rocky exoplanet. And so there's a couple reasons for this. First, from kind of a theoretical perspective, it's pretty tough to predict which of the bunch of rocky exoplanets that we know about actually would have atmospheres, because that depends on a lot of factors that we actually can't really observationally probe, like their entire XUV history that they underwent, or how much volatiles they started out with. And so the approach that we've taken kind of as a community is to go the other way around, observationally look for atmospheres on a bunch of small rocky exoplanets and figure out where we find them, where we do not find them, and kind of tease out from that information on where these atmospheres can survive or be revived over time. And so it's already been mentioned, it's kind of a very big focus in the exoplanet community. It has motivated the use of these 500 hours JWST DDT program to kind of delineate what we call this cosmic shoreline, which is kind of this theoretical dividing line that maybe we're going to be able to draw between where we would find planets that have atmospheres versus not. And also in terms of systems with rocky exoplanets, the TRAPPIST-1 system is very popular. I'm going to talk a little bit more about why. And there's been already a lot of observing time dedicated to try to finding planets around these, atmospheres around these planets in particular. And the reason why we're so interested in the TRAPPIST-1 system, or one of the many reasons why, is that, so first, very small star, which means that these secondary atmospheres would be relatively feasible to detect, but also because we have 7 small rocky planets around the same star, which means that they share a lot of these unknowns that I just talked about. They were around the same star for all this time, so it means that they share the same XUV history, for instance. And so while if we search for an atmosphere on any rocky exoplanet and we find it or don't find it, that just gives us some information for that system on maybe the amount of XUV it must have been under, or how much volatiles it started out with. The advantage with the TRAPPIST-1 system is that any constraint that you get on one of the TRAPPIST-1 planets on whether or not it has an atmosphere actually trickles down to updating the likelihood of atmospheric presence on all of them. But to do kind of this exercise, not all planets are equally, let's say, constraining for the planets that are further away from the star. For instance, even though observations for now point to no atmosphere on TRAPPIST-1d and perhaps no atmosphere on TRAPPIST-1c as well, what modeling has shown is that that doesn't yet really update our prior likelihood on our prior understanding of whether or not the outer planets should or shouldn't have atmospheres, because these are still relatively close to the star. It's been discussed TRAPPIST-1 is ultra cool star as well, which means that it had a very it has a very tumultuous history that the planets underwent, and so it's kind of unknown whether the other planets could have atmospheres. And so today I'm going to be talking about a planet a little bit further away, TRAPPIST-1d. So it's a pretty small planet, only 0.8 times the size of the Earth, very low density, just about 40% of the mass of the Earth. And it's right next to the habitable zone, so depending on who your favorite modeler is, they will tell you it could have liquid water, or water would be in the vapor state in its atmosphere. But essentially, what was also interesting in terms of understanding atmospheric presence in the TRAPPIST-1 system in general is that from modeling based on what we know already with TRAPPIST-1b and c, there's still about 50-50 odds, let's say, that this planet could or couldn't have an atmosphere. And so it means that getting constraints on this planet might maybe help us learn some things about the other ones. So as part of the nearest GTO program, we actually got 2 near-spec PRISM transits of this planet. This is one of the few near-spec observations that were kind of added to the nearest GTO. And so I won't be talking about flares, although there are flares in these observations. But if you have questions about that, we can circle back to that. But first, let's see what our transmission spectra looks like. So this is for the first visit. One thing I didn't mention is we observed 2 transits, like one right after the other. So the planet has an orbital period of 4 days, and we observed one transit, and then 4 days later, the other transit. And so we can already see that it's like not a flat line, but the variations you're seeing also don't really match what you would expect from a planetary atmosphere. This kind of slope that you're seeing here, it's kind of indicative. It's not something that you could really create with a planetary atmosphere. It's indicative of there being brighter regions of the photosphere that are not occulted by the planet as it passes in front of the star. So let's see what the planet or the transmission spectrum looks like just 4 days later. And here we go. And we kind of go back to this point that James was making earlier today about the fact that you're seeing a different star every day. The planet didn't change between these 2 observations, but the Y scale of these 2 plots is the same. And you can see that, again, we're seeing the signature of stellar contamination, but we can say that it's probably a very different distribution of dark and bright spots at the surface. And so one thing that we try to do to kind of get the most information from these observations is to not just use the information contained on the information about the stellar surface brightness contained in the transmission spectrum through the transit light source effect, but to also leverage the information contained in the out-of-transit stellar spectrum that we now have with near-spec from 0.6 to 5.2 microns. And so if you kind of think about this in terms of the components that go into, if you model let's say if you model the out-of-transit stellar spectrum as this kind of brighter component and maybe the quiet photosphere component, and then you model the transit light source effect, they depend on on the same parameters, essentially, like the spectrum of your quiet photosphere and the spectrum of your brighter component. But the way in which they probe them is different, which means that, in general, your out-of-transit stellar spectrum is pretty good at giving you the constraints on the temperatures of your different components. For instance, how much hotter the brighter component can be. And it also gives you an independent constraint on the photospheric temperature of the star that you have to assume when you do these transit light source calculations. On the other hand, what's interesting about the transit light source effect is if there was no atmosphere, you would just see a straight line if there was no stellar surface heterogeneity. And so this is actually much more sensitive to the fraction of the surface of the star that's covered by this brighter component. So kind of folding all of this together, if we try to get rid of stellar contamination the best as we can, and it's not really getting rid of it, it's kind of in our modeling, we assume that each spectrum has the same planetary atmosphere component and kind of different stellar heterogeneity components, and we marginalize over all the possibilities that we have there. We can get a constraint on how many high mean molecular weight volatiles could be in the atmosphere of the planet. That would be this axis, as a function of how thick the atmosphere that we probe is. And essentially, the fact that this part is colored here means that we get a pretty flat spectrum once we kind of correct for stellar contamination. And so that tells us that, I think, not a surprise, we can rule out these thick hydrogen-helium atmospheres. But what I think is really interesting is if we do kind of our best job at removing what we understand to be the signature of the transit light source effect, we get a spectrum that's kind of at the level where we would be able to detect potentially 1 bar high mean molecular weight secondary atmospheres and be sensitive to a lot of different molecules because of the wide wavelength coverage of near-spec PRISM. So just to kind of wrap up here, I'll give one example of one of the compositions that we looked at, and it's seeing how sensitive we would be to methane in a nitrogen background atmosphere. So something like the amounts of methane that you would be seeing on Titan, for instance, or that maybe the Earth had in its atmosphere during the Archean eon. And what we see is that in our case, we can rule out the amounts of methane that the Earth had in the past, but because of the haze layer of Titan, we couldn't rule out hazy Titan scenario because it would essentially also lead to a flat spectrum. And so the last thing, which was what I started out with, what can we learn about the other planets in the system, is let's say we go back to our kind of null hypothesis that this planet is actually a bare rock. That's why we just can rule out things and we just get a fairly flat spectrum. What does that mean for the other planets? And so we can do this exercise of starting out the same planet with different amounts of water and having that evolve over time. So having the water dissolve in the mantle and then perhaps outgas and be lost. And so we can draw a limit on how much water the planet could have lost over time, which for TRAPPIST-1d is a fairly small amount, which means that if it is indeed a bare rock, the inner planets of the TRAPPIST-1 system must have formed pretty dry, and the outer planets still have a good likelihood of having atmospheres. So I'll leave at my conclusion slides and take any questions.
What questions do we have for Caroline? Students first. Remember, these are outstanding pencils. You've never written with anything like this. You get 2 pencils, I guess.
Hi, Anish Babra, UC San Diego. Could you detect species other than water probably in the atmospheres?
Yeah, so if I just go back, I know I went through this pretty quickly, but this, what this plot shows here is essentially in the different colors which infrared species you would be sensitive to. Sorry, I went back somehow, yeah. So we explored a lot of things. There's water, which is the most affected actually by the transit light source effect. So it means that it's actually except for CO2 that has very small features, it's really the one where we can draw the least conclusions. But we have methane I talked about, but there's other things like NH3, SO2 that we could also probe. I think at this point we're just at the level where we can say we couldn't have like a 10 bar or 1 bar pure methane atmosphere, but we can't yet rule out all the scenarios, which is why kind of this part of that other diagram was like filled out. But yeah, if you just to show one thing, quantitatively, this is kind of the upper limits that we can draw. So you can see that for water, because of the TLS effect, we can't really rule out anything very conclusively, but for like methane or CO-rich atmospheres, then in this case, we can say that here is the kind of the 1 bar atmosphere. If it was just methane mixed with nothing else, it would have to be a very, very thin thing.
I have a question here at the front.
From online, is there any evidence for dark star spots for many TRAPPIST planets in the available JWST data, and how does this compare to expectations?
Yeah, so it's actually a complicated question to answer. I think the evidence for star spots is kind of like there could be star spots still in this spectrum. If I just go back, sorry, trying to go back one, yeah. If I go back, the kind of purple line is a model that would just have these bright regions, but the orange line is a model that would have both spots and faculae. And if you really, really want to fit every single thing, especially for the second visit, you can't make something that flat without having some kind of combination of brighter regions and darker spot regions. And so it may be that that's what we're seeing, but I think we can't really conclusively say whether we're seeing spots or not because of this degeneracy with just water features in the atmosphere.
Let's do another round of applause.